PowerPoint slides, you might have not understood how to find out the RS notation. So we are going to start with a simple molecule, and we are trying to fix the RS notation for this molecule. Take this molecule, C, H, CH3, COOH, and C2H5. How to find out the RS notation of this molecule? First, you have to number the various groups attached to the chiral center. This is the chiral center, because this is the carbon, which is connected to 4 different groups. So this is the chiral center, and I'm going to number various groups according to their preferences. The preference order is based upon the atomic number. So if you look at all these groups, here a carbon is attached, here another carbon is attached, here another carbon is attached. But you have to look into the next atom which is attached to the carbon. This carbon is attached to oxygen. This carbon is attached to another carbon, whereas this carbon is attached to another hydrogen. So the preference will be, this is the first preference, and this is given the second preference, and this is given the third preference, and this is given the fourth preference. So according to atomic number, we have given the preferences. Now look here, if I write the molecule like this, it is the Fischer projection formula. What is this Fischer? Actually, these two bonds are projecting towards the viewer. Actually, these two bonds are like this. It is projecting towards the viewer. Whereas these two bonds are away from the viewer. They are away. They are just to the next side of the blackboard. They are away from the viewer. So what I'm going to do, I want to bring this hydrogen here. I want to bring this hydrogen here. And after bringing this, I want to have the Fischer projection. Now look here, I can turn the molecule like this. I can make a turn. I'm turning. When I turn the entire molecule like this, what I'm getting? Carbon here, the hydrogen. Look here, this is projecting towards the viewer. So hydrogen has come over there. So the C2H5 has come here. This is C2H5. And then this CH3 has gone over there, right? So this is CH3, and then the COOH has come over here. Now the preferential order 1 is here, 2 is here, 3 is here, 4 is here. But this is not the projection. See, when you write a molecule in the Fischer projection, the horizontal arms should be projecting towards the viewer. So, in order to make the horizontal arm projected towards the viewer, I turn the molecule like this. See, first turn, it is in this plane like this. Second turn, I'm turning the molecule like this. So, when I turn the molecule like this, I'm getting what I'm getting. See, now, as these two bonds are projecting away from the viewer, now they projected towards the viewer, but COOH comes over here. This is COOH, and this becomes C2H5, whereas this remains here CH3, and this remains here H. Now the preference number, this is 1, this is 2, this is 3, and this is 4. Now I have brought the hydrogen down. At the same time, the Fischer projection is maintained. But watch closely. My idea is to bring the hydrogen down. So in order to bring the hydrogen down, I have turned the molecule like this. It is a planar motion. I have turned the molecule like this. When I turn the molecule, the Fischer projection, that is the horizontal arms are projecting towards the viewer. Now as I have turned, the vertical arms are projecting towards the viewer. In order to convert this into a Fischer projection, I have to make a horizontal rotation like this. This is the rotation in the plane. This is a horizontal rotation, so that this group will come here and this group will go there, but all the vertical groups are remaining in their own position. So what will happen? The horizontal arms are now projecting towards the viewer. This is the perfect Fisher projection without disturbing the molecular bonds, and the fourth preference is brought down. Now you rotate. Now you put the arrow mark starting from 1, 2, 3. See? Now the arrow mark rotation in the anti-clockwise direction. Therefore, this molecule is S configuration. This molecule is of S configuration. Are you able to understand now? So this is of S configuration. Now, a few more examples I would like to put so that you can understand very easily. Now look here, another example. Carbon, CH4, then OH, H, CH2OH. Now look, this is a chiral carbon. 18, 17, 20. So this is the chiral carbon because a carbon atom attached to 4 different groups. Now preference. With a high atomic number, so the first preference, both are carbons, but this carbon is directly attached to oxygen, so the preference number 2, whereas this carbon is attached to oxygen in the later stage, so this is preference number 3. Why this is given? See, both carbons are attached to oxygen, but why this is given much preference? Actually, this bond is something like this. So we can consider that this carbon is attached to 2 oxygens, whereas this bond is something like this: 1 oxygen, 2 hydrogens. So this is given the least preference comparing this group. Therefore, this is given the number 2. And finally, the number 4. Now I want to bring this 4 down. Now, according to Fisher projection, these 2 arms are projecting towards the viewer, whereas these 2 arms are away from the viewer. So I'm bringing it down by turning. So when I turn the molecule like this, I'm getting the hydrogen here, right? So the OH goes up, and then as it is turned here, the C2, H5, CH2, OH comes over here, and then CHO comes over here. But the problem is now this is not a Fisher. This is not Fisher, because here the vertical arms are projecting towards the viewer. Do not come late, gentlemen. I have to mark every time. Okay. Now this is not Fisher. In order to make this Fisher, I have to turn the molecule like this. So when I am turning this molecule like this, what happens? Carbon remains here. OH goes that way. Hydrogen goes away from the viewer. Then CHO comes here. C2H5, sorry, CH2OH comes over here. Now the preferential order 1, 2, 3, 4. So you put arrow mark according to the number order 1, 2, 3. Now this is clockwise rotation. This is R configuration. This is R configuration. This is how the RS notation is marked. Now you can take the mirror images of these molecules. I can write the mirror image. Watch closely. Let me write the mirror image of this molecule. You take this molecule and just interchanging carbon, Fisher projection, this side hydrogen, this side OH, and here it is CH2OH, and here it is CH4. I am going to put the preference number. So this is number 1, this is number 2, sorry, number 1, number 2, number 3, number 4. My idea is to bring the number 4 down. So I turn the molecule like this. So when I turn as a whole molecule like this, Those are. So what happens? Hydrogen comes here. CH2OH goes there. OH comes here. CH2. Now this is not a fissure. This is not a fissure because horizontal arms are supposed to project towards the viewer. So I turn the molecule like this. So when I turn the molecule like this, what happens? See, hydrogen goes away. OH is here. And then CHO here. CH2 OH here. Now number, this is 1, this is 2, this is 3, this is 4. So 1, 2, 3. So this is S configuration. Look here. This compound is of R configuration. This compound is of S configuration. So this is how the RS notation is marked. Now you can take another example of multiple chiral carbon centers. So wait a minute, I will bring a model and then I teach you. Then you can understand very easily. Wait for a minute, I'll be back. Now you can see, this is a chiral carbon. So blue, the green, the red, and white. This is a chiral carbon. Say for example, I can write a molecule and explain so that you can understand. Let me do it for lactic acid. Carbon, OH, H, CH3, COH. Look here. This is how the molecule is. So you are able to see. These two bonds are projecting towards the viewer, whereas these two bonds are away from the viewer. Are you able to understand? You should try to understand this particular thing. So the green and the white are viewing towards the viewer. The blue and red are away from the viewer. Now look at this molecule. I suppose you understand. Let me say the white is hydrogen, green is OH, right? Red is a CH3, and blue is a COOH. I suppose you understand now. The camera is clear. Okay. This is the lactic acid molecule. Let me adjust the camera a little bit. Suppose you understand now. Look. White is hydrogen, green is OH, blue is a COOH, and the red is a CH3. Look at the image. See? The white and the green are projecting towards the viewer, whereas red and blue are away from the viewer. Now, my idea is to bring the smallest preference down. So what I'm doing, I turn the molecule like this. So what I'm doing, see, I'm simply turning the molecule like this. I turn it. So hydrogen has come down, but it is projecting towards the viewer. And OH has gone up, but it is projecting towards the viewer. But these two groups are away from the viewer. What are they? When I turned like this, CH3 has come here, and then COOH has come here. Are you able to understand? But what is the fissure? These two arms should be projecting towards the viewer. So in order to adjust, I am turning the molecule like this. I suppose you understand now. I am turning the molecule like this. So what happens? Now This is COOH. This is CH3, whereas OH and H remain. Is it right? Now this is Fisher. So now what is the preference order? 1, 2, 3, 4. 4 is at the bottom. So I put an arrow mark according to the number 1, 2, 3. So this is less configuration. Suppose you look at the mirror images of this compound. This is carbon. Here hydrogen. Here OH. Here CH3. Here COOH. Now look. Actually, this was the original molecule. Now I interchange these two. Hydrogen is white, OH is blue. Is it right? OH is blue. Now I want to bring the hydrogen down, so I turn the molecule like this. Like this I turn. So the new molecule, what I'm getting is hydrogen has come down, OH has gone up, and then this is COOH here, then CH3 here. But this is not a Fisher because vertical arms are projecting towards the viewer. But by principle, the horizontal arms should project towards the viewer. So I turn the molecule like this. It is originally here. So I turn the molecule like this. So what happens? See, CH3 projects here. COOH goes there. But OH is here. Now the preference number 1, 2, 3, 4. So 1, 2, 3. So this is R rotation, clockwise rotation. So this is how the RS notations are made. Now, suppose if it has more than one chiral centers, what happens? Let me take the tartaric acid as an example and explain so that you will understand well. Okay. H, now, this is chiral carbon 1, this is chiral carbon. When you want to find out the configuration of the chiral carbon 1, you treat the entire group as a single substituent, a single group attached to the chiral carbon. So now the preference order 1, and this is 2, 1. This is carbon. Carbon gets oxygen. So this is 2. This is 3. This is 4. So my idea is to bring this carbon down. This one down. You can simply put like this even. So some group is attached. This entire thing is a group. So here it is COOH. Here it is OH. Here it is H. And this is first preference, second preference, the entire group, third preference. This is 4. My idea is to bring it down. So this is projecting towards the viewer, and this is away from the viewer. So when you bring it down, what happens? Here is the carbon. The vertical arms are projecting towards the viewer. Horizontal arms are away. So it has come down. Hydrogen here. This has gone up. This OH comes here, and COOH comes here. So what happens? This is 1. This is 2. This is 3. So 1, 2, 3. So this is S configuration. So carbon 1 with S configuration. 1s1. So 1 S. 1s configuration. Now you take the entire this part as a group and do it for the other things. Look here. Now I'm going to do it for the second carbon. This is COOH. This is H. This is OH. This is the entire group. Now, this is 1, this is 2, this is 3, this is 4. In order to get the 4th here, turn the molecule. So what I am getting, hydrogen here, COOH here, OH here, and the group here. This is not the fissure because previously this was the fissure. Now these two arms are projecting towards the weaver. So I turn the molecule like this. When I turn the molecule like this, what will happen? Hydrogen and OH will remain in their positions. But the third group and the COOH will get interchanged to get the fissure. Now preference 1, 2, 3, 4. So 1, 2, 3. This is R configuration. So this tartaric acid is 1s to R configuration. So the first carbon is S configuration and the second carbon is with R configuration. So 1s to R configuration. Now look here. So this is 1s, this is 2R. Both the carbons are having different configurations, and because of this tartaric acid is optically active. Suppose if we take a mesotartaric acid, let me say what happens. This is 1s 2R configuration. OH, OH, H, COOH, COOH. Take this entire group as a group. So OH, H, COOH, and then this group becomes 1, 2, 3, 4. This has to be brought here. So what you are getting is H, and then the group here, OH here, COOH here. This is not fissure. I turn the molecule. So what I am getting, this group comes over here, COOH, OH, H. So what? 2, 3, 4, 1, 2, 3. 1R configuration. If you take this one, now this is an entire group, OH here, H here, COOH here. Now this H has to be brought down. So I'm bringing the H down. COOH, then OH here, then the third group is here. This is not the fissure because these two arms are projecting towards the weaver. So I turn the molecule like this. So what I'm getting is, as a result of this, H, OH, here comes the COOH, third group. So 1, 2, 3, 4. So 1, 2, 3, 2 S. So it is 1R S. So this is how configurations are made. I suppose you might have understood what I thought. Any clarification? Any doubt you have?